Good morning. Here we are once again. It is the physics video lecture. Physics 105B, video lecture 40. And we're going to move on into a new topic, fluid mechanics. And we're wrapping up the semester, so I think I'll do a few hours before we do a complete review. But this is an interesting topic, and it puts things in perspective, and it can motivate some further work that we could all do. So let's start with some basics. So we've got fluid mechanics, and first we're going to just place it into context and then start with the really basic properties. So if we go to what we've been studying so far, I'll make a typical list. So we start with point mechanics. That's what we have been studying all of these 2 semesters. And in the first semester, 105A, we did mostly, or pretty much exclusively, one particle system. So then we had Newton's law and everything that follows. And then we can go from point mechanics to systems, or what we call point systems, systems of point particles. And then we'll just add a subscript here. So we've got a system of point particles, and we could say we had an external plus all of the, let's call that J, all of the internal forces as well. So Fij, and point systems. Now, if you think of a point system in which the relative distances separating all those points remain constant, then you have a rigid body. And we've also studied that. And although you have many points, you reduce the degrees of freedom considerably because all the points are, because the body is rigid. Okay. So after that, we could imagine that we've got a rigid body that's not fully rigid and that can be distorted. So instead of this being a rigid body, it's something that can be bent and twisted, okay? And that would be elasticity theory. So in this case, the points are not all fixed, but they can only be displaced slightly. And elasticity theory is a field theory. We'll get to that in a moment, a little bit more. I just want to complete the list with the fluids. So here you're still talking about solids. If you go to fluids, gas, or liquid, then sure, it's fundamentally a point system at the molecular level, but these points can move with respect to each other freely in a certain way. So these 2 are actually a field theory. So here you have a displacement field, or a strain or a stress field, and here you have a velocity field. This is what we're going to look at. So you have a sort of a progression here logically until you get to the fluids. I'll say a couple words about elasticity. As I just mentioned, you have stress, you have strain, you have displacement. So yeah, just to mention these things, stress, strain, etc. You end up with systems of linear equations, partial differential equations, because, as I said, it's a field. And you therefore have oscillations, waves. Geophysicists know about these things because there are different types of waves in a fluid and in a solid. Different types of waves. Different types of waves in earthquakes, for instance. Okay, good. So that's elasticity. That's not what we're talking about in these next few hours. So if we're talking about fluids, then we're talking about a velocity field V, and it turns out the equations are, for the most part, nonlinear. And that brings its own difficulties. And a lot of work in fluids is done numerically. So what we'll do is we'll set the equations up, the partial differential equations, do a little bit with them, but that would be the foundation of any kind of numerical work you end up doing in fluid mechanics. So nonlinear equations. Good, so that's for starters. So let's continue the characterization of the fluids a little more systematically. So once again, the relation to point mechanics can be stated as follows. So we have atomism, and so we know that in a very small volume there is still an enormous amount of particles. Okay, so suppose you had some little cubic millimeter, and you still might have 10 to the 18 particles inside. And the same, you know, with a gas, a couple of orders of magnitude smaller, but still an enormous amount. So you can start to think of these, yeah, but we got some color. You can start to think of that as a continuum if your infinitesimal element, so you're going to do calculus, if your infinitesimal element is small on the macroscopic scale, but large in the sense that it still contains a whole lot of individual particles. And you don't actually specify how many, but it's just a judgment call, okay? So, because of this, we have the infinitesimal element, we'll just call it dV, d volume. Infinitesimal volume element, d volume, contains many particles. Without specifying how many, we know that it's a lot. Any way you look at it. So, and that would also give us the limits of validity if we were extending our analysis too far into the microscopic realm, then things might be expected to break down in terms of our partial differential equations that we haven't derived yet. So, but that we will derive. Okay, so once again we have this, and we have the fluid, as said before, characterized by a velocity vector. So we've got a velocity vector field, V. So it's a vector field, so this velocity vector, X, Y, z, and t, and our task is to find differential equations for this and to be able to solve them based on basic laws of mechanics. So we've got the velocity field, and one could even say a little bit right now. So here we are, say, in our 2 or 3-dimensional space, and we have a fluid flowing. Okay. So at any point in that fluid, there is a velocity. What I've just drawn is a streamline to a velocity vector, but there's a vector field any point here. And so if the explicit time dependence is not there, then you could actually have a streamline like this. If the explicit time dependence is present, then this vector would change in time at that location. Okay. Good. So fluid's characterized by a velocity vector, also pressure, P, X, Y, Z, and T. So pressure is a scalar, velocity is a vector. You could have density, rho, X, Y, Z, and T. You could have temperature, and in fact you could have other thermodynamic quantities. I'll put temperature here. These are thermodynamic quantities, and so they'll actually be linked, and I could also add entropy, but they will be linked by some equation of state. Okay. So they will show up in the equations of motion. And it can get pretty complicated if you start adding temperature and energy dissipation to the mix. So I think I'll say something about, I'll write something down. Yeah, so put a note here. These are thermodynamic quantities. So generally 2 of these will suffice, and then you can get a third one via equation of state. 2 suffice to obtain a third via equation of state. Okay. Good, so then we have to start talking about properties of these. One more important point, almost missed it. So are we numbering things? Yeah, how about we number these things? So we had atomism. In that discussion, that we have the fluids are characterized by, and what's going to play an important role is the way, what kind of interaction there is. So what we have is a fluid is going to be a neutral fluid for the most part. So let's say something about the interaction. So the interaction between fluid elements is via short range forces. So interaction between fluid elements, very important point. So via short range, I'll underline that, short range forces. So if you have 2 fluid elements, I'll just draw a square, a cube, and they're actually adjacent to each other. So they're pressing up against each other. Put a third one in here. You guys draw a better picture. Then they're interacting via their surfaces. Okay, so if you have an element, you have the interaction via the surface. as opposed to a charged fluid. So if in addition to this being a fluid, it were, say, a plasma with charge, or just a charged fluid in general, you would have to add the equations of electromagnetism to the equations of fluid mechanics. And that exists. It's called magnetohydrodynamics. And that makes things a lot more complicated. But yeah, so short range forces and surface forces, that's an important point. I'll put a star here. Good. Yeah, so with these ingredients we can get started. And we'll get started with the conservation of mass. Yeah, good. Conservation of mass and the continuity equation. And nothing fancy here. We can imagine flows through a tapered channel, a water hose, a nozzle, that type of thing. So I'll just say a tapered pipe, just so we have something concrete to look at. And if it's an incompressible fluid, we'll be sure that it's flowing slower here and faster through the taper, and we've all, I'm assuming we've all experienced that. Okay. So slower, faster. And that's actually an expression of the conservation of mass. So a little more formally, we'll put a cross-sectional area here and here. This is how you look at it in physics 4A. So you've got areas of 1, areas of 2, and then you can say that dm for mass dt is going to be equal to a density times a velocity, okay? Because we have times an area, okay? Because we have kilograms meter cubed, and then we have, this is a V, velocity, not volume, okay? So we have meters per second, and then we have meters squared, so we get kilograms per second. Kilograms per second, mass per second. It's right here, conservation of mass. And so in terms of these points 1 and 2, we have rho V A sub 1 is equal to rho VA sub 2. So we're just assuming a velocity vector just in the one direction, nothing fancy here, right? As of now. If the density is constant, if rho is constant, which it often is, then we could have V1A1 equals V2A2. So that's the basic discussion of the continuity equation. So yeah, let's, all of these here, this and this here, continuity equation. So at this level, there's a favorite little example that we'll look up, we'll discuss real quickly. of course, the first example is the water flow through a nozzle. If you have a hose with a tapered nozzle at the end, you've seen before how that works. And I should say, if you hold the nozzle or the hose without the nozzle and the hose with the nozzle vertically, then the speed with which it leaves the pipe or the nozzle or the hose can be calculated by how high the water goes, just from the law of free fall. Okay. So that would be an example for you guys to consider. But yeah, you could just put that note right up by that picture, because that's basically what's being described here. So there's another interesting phenomenon, and that is if you have water flowing from a faucet, no aerator, just a small amount, you actually see it come down and taper. Okay. So my second example is, okay, we have a faucet here, and there's water flowing out of it. And I think we've all seen this. It tapers, and when it gets too thin here, it'll break up into drops. So this tapered aspect, so this is the faucet, we ought to be able to calculate that. This water, as soon as it leaves the spigot here, it's under the influence of gravity, and it's just in free fall. Okay. So if we have A1, V1 right here, and somewhere down farther, A2, V2, then we have pi R1 squared V1 equals pi R2 squared V2. But V2 can be obtained just from the law of free fall. And it's going to be V2, it's going to be depend on V1 and the distance that it's fallen. I'll have to give that a name. Maybe H. And that means you can find R2 given R1. Okay. So find R2, and therefore you have the function that describes, the curve that describes this taper here. Okay. R2. Boom. So that's an interesting problem. And if you actually experiment with your faucet, it's hard to get a perfect trickle, but you can often set up a pretty good one. Okay, so that's the basic version of the continuity equation, and we want to look at it a little more technically now. So okay, so we had that flow picture with the taper and the nozzle. So now let's look at the following. Flow through a surface. Okay. What we had before was just, we had the taper, okay? So we could have thought a surface, a cross-sectional surface. But now we'll just talk about the flow through a general surface. Say that we can imagine an imaginary surface within a flow field. And then we have the same expression, rho v, but we'll integrate it. Okay. Rho v d area. And since the velocity is a vector, and the area element is a vector also, we can think of a surface normal, and then we're talking about rho v dot n hat d surface area. Okay. So that's the flow through a surface, and if this is a volume, then we could say it's the boundary of the volume. A nice formalism there is just to refer to a volume, and this del in front of the volume just refers to the surface that bounds that volume. So we'll probably use that here and there. Okay. So there's a flow through a surface. On the one hand, make a list here. On the other hand, we have the fluid contained within the surface. So fluid enclosed in a volume. Volume V. So what would that be? That would be the integral of rho d volume. Mass per volume d volume, so that's the mass enclosed within the volume. And that's the flow through the volume. So this was, as we saw before in our dimensional analysis, this was mass per second, and this here is just a mass. So fluid enclosed, free, fluid that leaves a volume. Is going to be the change of the, yeah, we'll just say that leaves the volume. We've got d, in fact, we'll put it in the integral d dt rho d volume. Should have been a v right here. Volume. Okay. So what we're going to do is equate the change with respect to time of the fluid enclosed in the volume with the fluid that flows out of the volume. Okay, so we're going to equate those two. And see what happens. Okay. You know, for this definition, we go into the integral, but first we'll write it outside. That's more consequential. Okay. Next step, we'll take it in, but here we had people. Okay, so what we're going to have here is integral over the boundary of the volume at the area. Now, this is an outer surface normal. Okay, so this is the fluid that leaves the volume, and therefore it's going to be this is just the change. This was just the rate of change. Change. So that's the change of the mass. That's the time dependence of the change of the mass in the volume. Okay, I was getting ahead of myself there. This here is the fluid that leaves the volume because of the outer surface normal. Okay, the outer surface normal, there's a, and if V is parallel to n hat, for example, then you get the plus sign there, okay? So this is positive. On the other hand, if the fluid is leaving the volume, then the mass in the fluid in the volume is decreasing, okay? So this gets a minus sign. So we're going to get minus integral d dt rho volume. Okay, so that's why we put the minus sign in there by hand. And now we'll use Gauss's law, and we will get integral divergence of rho times v d volume equals minus, and then we'll go ahead, take this inside d volume, and we'll combine the two expressions, and we'll get integral d rho dt plus divergence rho v d volume equals 0. Now, this is an arbitrary volume in, within some fluid flow, and because it's an arbitrary volume, we can claim that the integrand itself vanishes. That was just like in the variation calculus. And so I'll just write here arbitrary V, and that gives us the continuity equation. This is what we were after. So that's the continuity equation, one of the equations of fluid dynamics, and you can see the first one. Okay. So continuity equation. And let's see how we're doing time-wise. Excellent. Okay, so now we have the continuity equation. This is what we were looking for when we were doing Louis-Vier's theorem back in Hamiltonian mechanics. So I think that's what I'm going to discuss next again, just to make up that omission. So I'll remind us what we did. We invoked this back then, so this is just a reminder. Good. And let me put a note here as well. So, if the fluid is leaving, okay, then the mass inside the volume is decreasing, okay? But if the fluid is leaving, you have a positive sign here. As said before, therefore, we had to put that minus sign in by hand. Okay, so note, if fluid leaving the volume the mass inside is decreasing, okay? But again, if it's leaving, this is positive, okay? Therefore, if the mass is decreasing and this is negative, we get the other negative sign that gives both signs positive. Okay. That's the reason for this. Okay. So now let's look at the continuity equation a little more. And this is pretty much just one step. And that is, that's just a note under the continuity equation now. If rho is constant, okay, so if you have an incompressible fluid, then this derivative vanishes. You can pull rho out of this divergence expression here, and then you have the divergence of V is equal to 0. So if rho is constant, then divergence of V is equal to 0. So this is the differential equation for an incompressible fluid. Okay. Or you can say it's the condition for an incompressible fluid. And when we had Louis-Diet's theorem in Hamiltonian mechanics, we had a divergence of a 2n component vector composed of positions and momenta, and that divergence vanished. And that allowed us to say that the phase flow, the phase fluid flow of phase space, okay, the phase fluid is incompressible. So incompressible fluid, and I'll just put here recall. Hamiltonian mechanics. Louis-Diet's theorem. The phase flow is, or the phase fluid is incompressible. Here, I'll put those both in words. Phase fluid incompressible, or the phase flow preserves volume. I have a really great proof of this, by the way, extended rigorous mathematical proof that does not invoke this divergence theorem here. But this is kind of nice to bring it into play this way. So there we have the divergence of the vector q1 to qn, p1 to pn was equal to 0. And of course you were in phase space QP, but we had seen that there's a vector associated with every point in the phase space. Okay, so yeah, anyway. So that was something we had to do, right? And we did it. So let's see where we are. I think this is a good place to leave off. Well, we can do a little bit more. Or I'll set up what we're going to do next. Yeah, I'll just set up where we're headed next. So yeah, we have, well, I can put it this way. We have one differential equation for a fluid, continuity equation. It has 3 quantities and a 4th. So we have one differential equation for 4 quantities. Clearly not yet there. Okay. So what we'll talk about next is force and pressure. Pressure in a fluid, force on a fluid element. So next, force and pressure. And again, we'll just start with the basic ideas of force and pressure. You know, we've learned that pressure is force divided by area, right? It's units, newtons per square meter. And in a fluid, we have to know something else, because force is also, this is just magnitudes and dimensions, but of course the force is a vector. The pressure is not a vector, okay? So what we say in a fluid, we say that the force due to a pressure acts in the direction of a surface normal, okay? So if we have, say, a fluid here, and we'll start with a cube, then the forces due to the pressure in the fluid, how about another color? It's going to be perpendicular to the surface, or in the direction of the surface normal, like that. And if you have a shape that's not just a cube, then you'll have pressures in all of these directions here. Don't ask about the point. It's just a point. Okay. Okay, so that's the one thing. And then we have Pascal's principle. That the pressure is transmitted uniformly throughout the fluid. Okay. Throughout the fluid. So Pascal. So if you were to press down on this, say with a so you have the piston, you have the seal there, and then the pressure that, the force that you're exerting down would be transmitted throughout the entire fluid. And of course, the force would be the pressure times the area. Okay, so you have area here, force you put on there, pressure is given by that force divided by that surface area. Okay. And I think I'll just end with a little hydraulic picture. We can just call this basic example. We'll call this hydraulic lift. And we'll just have two here. Make them both the same height. Okay, so we've got fluid in here, and we've got some kind of piston. So we can press down here. And we've got another one here. Press down here and it'll push up here. So either direction is possible. Okay. So we're going to have F1, F2. If you press down F1, this one goes up and vice versa. Well, we have different cross-sectional areas. F1 and F2. But we have, I'll save the blue for the fluid. We have cross-sectional area A1, A2 here, and then we have Pascal's principle that the pressure within this fluid is uniformly distributed. Okay, so the pressure is the same everywhere. So what we have is, okay, so, oops, wanted blue. Okay, so what we have is the fluid in here, and by this basic principle, pressure, which is the same everywhere, is F1 over A1, and it's F2 over A2. So sure, F2 over F1 is simply A2 divided by A1. Or if you want to, this is actually good enough. So the ratio of these forces is as the areas. And this is, of course, a type of mechanical advantage, and you're going to have your, your work is still going to be the same. So yeah, let's go ahead and finish that up. So say you do some work, and that's your pressure times your change in volume. But your change in volume so you got the pressure, your change in volume is going to be A sub I delta X sub I. So the point is that, right, area times the length is a volume. You're going to have that mechanical advantage out of this relation here, but you're going to have to press, say you want the 10-fold mechanical advantage by pushing down here, and the hydraulic pushes up there, you're going to have to push down with 10 times the distance, right, in order to get 10 times the force up here. Okay. So I'm just going to write mechanical advantage in scare quotes. It is mechanics, maybe we could call it hydraulic advantage, but you get the idea. I'll just put here, since we're looking for the advantage, I'll just put over here, we could have F 2 is equal to F1 A2 over A1, which in my picture is very small. Okay, A2 over A1 is tiny, so this is a small force, and it delivers a huge force over here. That's basically it. That's probably a good place to stop. So next time, after this elementary thing, we'll go ahead and do force and pressure in the sense of Newton's law and get the next equation of the field. Good. See you guys next time.